All right, the next example we have is example 2. Example 2 is one of these problems where it looks a lot worse than it actually is. There's a lot going on in this problem as far as notation, so you just want to make sure that you're able to read the notation adequately. So we're given a function, a scalar function, and we're asked to evaluate this monstrosity. And as far as notation goes in math classes, when you're taking the calculus sequence, there's some notations that can be just a little bit overwhelming. In Calc 2, I would think of it as like the summation notation when you're doing series. Um, and then as we do multiple integrals and we start adding these symbols here and here, it can get a little bit difficult just to remember what everything's actually saying. So what's actually being said here? So we know what f is, so we know what this f is referring to. It's just referring to this. We know what this symbol means. When you take this symbol and have it act on a scalar function, this is going to give us the gradient of this function. So we can take our x, y, and z partials and put them in there. So we could do this. So that's the gradient of f. So remember that the gradient of f is in fact its own vector field. The gradient of a scalar function is a vector valued function. It is a vector field. So this right here is a vector line integral. Because it's a vector line integral, we're integrating over some path c. So the first thing I want to really talk about here about this path c is this is the only text that we have in this problem. It doesn't tell us anything about c. Not really. The integral does tell us something about c. This symbol here, this loop, is telling us that the path c is closed. So c is some closed path in 3 dimensions. How do I know it's a path in 3 dimensions? Well, because this function f has 3 variables. So the gradient of it is a vector field that has 3 components and 3 variables. And in general, when you integrate such a function, that path has to be in the domain space. So I know that this is closed because of this loop, and I know it's in 3 dimensions because of the fact that little f has 3 variables. Okay, well, because they didn't tell us any other information about c, there's no way that we could possibly come up with some r of t. There's no way to actually figure this out. It's not possible to write this down because we do not have sufficient information. We don't even know what the endpoints of the path are, let alone what kind of path it is or what it looks like. So we cannot write down some r of t. So these are all clues to us that we shouldn't actually be trying to do this. So the previous example, example 1, also is in the same vein. This problem, the whole point of it is to think of the fundamental theorem for conservative vector fields. So the fundamental theorem of conservative vector fields says, as a recap here, if C is a path beginning at some point, let's say P, and ending at some point Q, then if F is conservative. So remember, what's it mean to be conservative? A vector field's conservative if it is the gradient of some scalar function. So we actually do know that because this is what we're asked to integrate, this is telling us that this is conservative. So the fundamental theorem for conservative vector fields applies. So if that's true, then the line integral over C, f dot dr, which is the same thing as the line integral gradient of f dot dr over C, this is f of q minus f of p. But if p and q are the same, in other words, the path is closed, the endpoints are the same, then this integral if these two things are the same, this has to equal 0. So for this entire problem, it should be 0. Why? The justification is this is conservative, and C is a closed path.